Okay, today we're going to be talking about conductors and insulators. Now, we know that we have two types of material that you'll have come across. And they're either conductors or insulators. And we're going to soon be discovering there's a third class called semiconductors, and there's another class called superconductors as well. But this is what you will have been familiar with. In conductors, they conduct heat and electricity. And insulators don't conduct heat or electricity. Now it's interesting that things that don't conduct heat also don't conduct electricity, and likewise things that do conduct heat also conduct electricity. That the mechanism for both types of conduction, there must be some underlying mechanism which is the same in both. So for electricity, we need to have we need current to be able to flow. And so we need current to flow. Not in insulators, in conductors, sorry. Therefore, electrons are free to move. In a perfect insulator, all electrons are tightly bound. And therefore can't flow, can't move. So that's why you don't get a current flowing through an insulator. So to look at this more fully, we're actually going to look at the structure of copper. So copper is the atom that is the element that the cables in your home and in your lights, if you were to strip back all the wiring in your home, you'd find copper cables. So let's think about what the copper atom looks like. So here's our copper nucleus, and then we have, surrounding the nucleus, we have our electrons. And our electrons are in very specific energy levels. So in the first energy level, we have 2 electrons. In the second energy level, we have 8 electrons. 1, 2, 3, 4, 6, 7, 8. In the third level, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18 electrons. So let's draw our 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. They're a bit squished in here. Now, for copper, which is a metal, this outer level, on all atoms, the outer level is the one which is going to give us the most information about how this atom is going to bond and interact with other elements. And on copper, we have 1 electron. And this means that most of this energy level is empty. Now, all chemical bonding comes from an atom trying to fill its outer energy level. So this outer level is called the valence level. And this electron here is the valence electron. Now, if you were to look at chlorine, let me just remind myself of the atomic structure of chlorine. Now, chlorine is not so this is going to be chlorine. Chlorine's not a metal, it's a non-metal. And so this is our nucleus. And again, the inner level always has 2 electrons if it's full. The next level is going to have 8 in it because it's full. 1, 2, 3, 4, 5, 6, 7, 8. And then the outer level has 7. So 1, 2, 3, 4, 5, 6, 7. This here is empty. So what happens is chlorine atoms will come together. You'll get a chlorine atom and it'll bond with another chlorine atom, and they'll share an electron in this space here, and therefore that's how it fills its energy levels. And this is called a covalent bond, and that's how non-metals bond together to fill up their outer energy level. Metals, they've got a lot of empty spaces, and therefore they don't bond like this. So what a metal does is they share their outer electrons. So this is our copper atoms, and they're all beside each other in a big kind of lump of copper. And what you see is, remember our valence electron, one electron in its outer level. And these atoms will just share these electrons. So they're now free to move. And that's why, and this is the same for all metals, different metals will have different numbers of valence electrons. But they'll all bond in a very similar way, where they'll essentially give this electron up. It's easy to unbond. It's not tightly bonded to the atom. So here you've got these copper, basically ions, held together in this soup of electrons. So in a metal, the valence electrons, now remember, valence electrons are the electrons on the outer shell, are not tightly bound. Now, when we look at let's go back and look at our copper and our chlorine. Looking at these diagrams of all these atoms, we're not really interested in the electrons that are on the inner energy levels, because these are all full. They're tightly bound. They don't want to really. You're not going to get this electron just flying off out the atom, because it's very happy here in its energy level. It's stable. But it's the valence levels that we're going to be interested in. So instead of, when we're thinking about conductors and insulators, instead of drawing all the different energy levels of all the different electrons, we're going to simplify it by talking about energy bands. So let's think about an insulator. So we've got 3 different energy bands. We've got the filled band, we've got the valence band, and we've got a conduction band. And we've also got a band gap. So in an insulator, we've got, wait a minute, I'll draw it a bit better. Our filled band. So that's all those energy levels from the nucleus out to the valence band, the outer band, that are just all, they're full of electrons, they're tightly bound, and they're just in that stable place. Then you've got this valence band. Now remember, the energy levels are set that those electrons can only take specific levels of energy. When we look at, let me just show you again, the gap between these different levels, the electron's not going to sit in the middle. It has to take these set levels of energy in the atom. So our valence band is that outer level where we've got our outer electrons. So the filled band is full, and the valence band can be full or partially full. So if you think, most insulators are going to be, they're going to form a bond with either, like for example, two chlorine atoms are going to come together and share one of their electrons to fill up their valence band, or they might bond with another element. So you're going to see in the insulator, the valence band will either be full because there's bonding happening, or they'll be partially full. And then you get up here, the conduction band. So this is a place where you've got free electrons that can carry a current. And in this point here, you've got a band gap. This is the amount of energy that you would have to give an electron in the valence level to jump into the conduction gap. It is possible to force an insulator to carry a current, but you need to give a lot of energy because they don't want to give up their electrons. They're so close to getting that outer level full, so they're not going to readily give up an electron. But if you give enough energy, that electron will be forced into the conduction band. And this band is this is the gap of how much energy you need to feed that to get that electron free so it can now conduct electricity. And so this here, up here, is the relative energy. So our conduction band is where electrons are free to conduct current. So now we're going to look at a conductor. So we still have in our conductor this filled band. So we just quickly look back at our copper molecule. So you've got all these energy levels, or copper atoms, sorry. These are all filled, they're nice and stable. These electrons don't want to be pulled out because they're in a stable place. So these here are our filled bands. But then you have, I'm going to change colours actually. So we've got our valence band. Oops, there we go. But we also have our conduction band. I'll make that a bit brighter. And in a conductor, the conduction band and the valence band, they overlap. So here is our conduction band. So the filled band is still full. So this is full. Our valence band can be partially full or it could be empty. So if you think about, let's look back on our, let's get rid of that one. Our copper molecule, this electron here, at any given time, it might be free. It might be off here and it might be conducting electricity. Or it might jump back in and be in its energy level. So in that valence level would then be partially full, but then if that electron is knocked out and is just here part of the electrons that are conducting the electricity, then that valence level is going to be empty on that atom. And because the electrons are constantly moving, the state of this valence level is going to be in a constant state of flux, as if you think about this electron here, that could jump back into its valence level, then it'll jump out again. So this is a really fluid system, and that's why the valence band and the conduction band in a conductor have this overlap. Now, temperature is important. So more thermal energy that's going to lead to more energy for electrons to move. And so you're going to see more of those electrons knocking out of their valence level into the conduction level. But even in an insulator, if you give it more thermal energy, because of the band gap, it's going to be very hard to close that band gap for there to be a flow of electrons. Now, let's look at applications for conductors and insulators. Obviously, let's think about energy pylons. These conduct electricity at very high voltages. So they have, the cables are connected. If you next time you're driving past energy pylons, the cables are held to the pylon by ceramic, sometimes glass discs. These are insulators, and they protect the pylon from becoming charged. the cable itself, this cable here is actually aluminium. I can't spell aluminium, because copper's heavy. Very practical reasons. So the cabling in your home, the wiring in your home is copper cables, but this is going to be aluminium because aluminium is really light, plus some steel to give it strength. Now, cables are made of thin strands instead of a thick cable. So I'll explain in a minute why that is. Made of thin strands to overcome skin effect. Now, what is the skin effect? Now, if you were to look at just a piece of metal cabling and you were to explore its resistance, you would notice an increase in diameter gives a decrease in resistance. So you would think if you had thick cables up here, that would be good because you want to lower the resistance so the current can flow. However, this is an AC. In an AC power supply, current will flow on the surface. So when you're dealing with an AC supply, it's the surface of the cable that's going to carry the current. And when you increase the diameter, and you're in this situation where you're sending very high voltage of an AC supply, increasing the diameter will actually increase the resistance. So by having a thin wire and taking lots of thin wires together and building your cable that way, you can counteract this skin effect that you have with the AC supply. It's the skin effect is greater at high frequencies. So mains voltage in the UK is at 50 Hertz. Frequency of 50 Hertz, and that's another way to counterbalance the skin effect. So I hope that helps and makes sense.